Okay, so we're starting a new unit today. So this is Unit 4, Day 1. Hopefully you appreciate my attempt at some pastel colors for Easter. And we're actually going to start the day with Desmos Activity. So I'm just going to get you started on this Desmos Activity, then I'll ask you to push pause in a second. So remember to do this, you're going to go to student.desmos.com and type in this code, B7968G. Now don't go there yet because I want to just show you what is going to happen. So you're going to type in the code. I'm not going to actually go in there because it'll make me a student. But when you sign in, please sign in with your regular name so that I'll be able to see that you completed this. Don't put some joke name. So just throw in your regular name and then you'll get to this first screen. So I'm just going to show you the first few steps in this first screen. So we're actually going to be investigating the derivative of exponential functions now. So we've been doing derivatives of polynomial functions, things like a quadratic or a cubic and a linear function, what the slopes of the tangents are for that. But we don't have a rule for taking the derivative of exponential functions. So this is what you're going to explore right now. Try and figure out what the exponential function looks like. So we'll go back to what we did before, where we're actually going to graph the slopes of tangents and investigate what the shape of the derivative is. So you see I've got an exponential function there in red. It's 2 to the power of x. And you see I've got this as the tangents. Okay? What you have here is the y value of the exponential function. So if we go to, for example, 0, or sorry, yeah, a equals 0, so 2 to the power of 0 is 1. So there's the y value. But I've also added the slope of the tangent at that specific point. So that's the green tangent there. So you're going to go off and investigate all the slopes of the tangents at the different points. So I started this at -3. So we're going to fill in this table. So first, I'm curious, what is the actual value of the y value of the red graph at this point? So it's 2 to the power of 3. So you're going to, or -3. And apparently that is 0.125. And then you're going to go off and evaluate the slope of the tangent at that. So it's a very thin, low, flat line here. And it's right here, so the tangent is 0.0866. And 4 decimal places is fine, so that'll be enough. And then we're going to go over here and move it over to a equals 2 and find the y value for that is 0.25. And the slope of the tangent is a little bit steeper. It's 0.173, I'll round it to 33, okay? And then move on to a equals 1 and repeat, okay? So that's what you're going to do to explore the slope of the tangents and find the derivative of an exponential function, in particular this 2 to the power of x. I'm going to leave you at that. So you're going to pause the video now and go to student.desmos.com and enter this code and try that activity. And please try the activity before you move on to any more slides. So push pause now and come back and push play when you're ready to go again. Okay, so hopefully you enjoyed that activity and maybe discovered some very interesting features. In particular, you went off, and this is just a rough draft of what happened there. So the first thing you did was you looked at the slope of 2 to the power of x, and you found that the slope of the derivative looked like another exponential function, which was really neat. Okay, so unlike with parabolas where the slope of the derivative or the derivatives were linear, there were one less, the derivative of exponential functions behave very differently. They actually produce other functions that look like exponential functions. So the slope, or the derivative of 2 to the x ended up being this smaller one. So it's very close to the shape, but a little bit lower. And then you went off and did 3 to the x, which was interesting, and it produced a graph that was above the original. So then it lends the question, I wonder if there's a base that was somewhere between 2 and 3 where the slope of the derivative or the tangents of the derivative looked exactly like the original. And for no apparent reason, I asked you to put in 2.71828, da 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 da. And it turns out that the slope of the derivatives equals the actual y values. And therefore, the red derivative is exactly the same as the original. And that produced this special function, or this special number, e. It's called Euler's constant. It's pronounced Euler. It's named after a mathematician, Euler, who discovered it. And the Euler's constant is a non-terminating, non-repeating decimal that goes on forever and ever. But we can approximate it to about 2.718 is the common number that we use. Just like pi is 3.14, well, we have a new one called e, which is 2.718. So that's how we first discovered it. But to find the actual number out, he did this. He did a different way to discover it by taking the limit of 1 plus h to the 1 over h, and discovered that as this gets smaller and smaller to 0, you get this constant e coming out. Now, we don't need to know anything about this. This just happens to be part of the definition. We just need to know that Euler's constant produces this e, which is very significant. And the reason it's significant in the calculus world is because e to the x, the derivative of e to the x, is itself. So 2.718 blah, 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 blah to the power of x, when you take the derivative of it, it's exactly the same as 2.71 blah, blah, blah to the power of x. So this is a very significant one. So we have the only exponential function we've been able to differentiate today is e to the power of x. But we'll see how that gets into being able to differentiate other exponential functions. So if I give you an equation like y equals e to the power of x, the derivative is e to the power of x. Probably the easiest of all the differentiation rules we're going to learn. So let's try this in a bunch of different scenarios. So e to the power x is the basic exponential function, but we're going to look at all sorts of different exponential functions. And the key is all the rules that we've learned about differentiation apply to this exponential function. So I'll give you a second to write that down, and you can pause the video if you'd like. But now I'm going to start going off and answering them. All right, so y equals e to the power of x. So what's the derivative of that? We're going to differentiate this. Well, if y equals e to the power of x, the derivative is e to the power of x. Pretty straightforward. Here we have a function y equals 5 e to the x. Now, before I solve this, I want you to remember one of our other rules. So if we had 5x squared, I know you know the derivative of that is 10x. But where does it actually come from? Well, you actually you ignore the 5. The constant rule when differentiating here says that you leave those constants alone if it's in front of a variable. So that 5 actually stays there, and you differentiate the x squared. The x squared, the derivative of x squared is 2x. And so then you multiply the 5 and the 2 and you get the 10x. I know we usually go from here to here, but we actually know that the constant stays 5, and then you differentiate this. So if differentiating y equals 5 e to the x, then the derivative is 5 e to the x, because the 5 is just the constant in front, the coefficient, excuse me. I keep saying constant, it's the coefficient. The coefficient stays the same. The coefficient stays the same, okay? And when you differentiate, the coefficient doesn't influence it. So here's the coefficient is 5, so the 5 stays there, and the derivative of e to the x is this. Moving on to C, y equals e to the 7x. Again, before I differentiate this, I want you to remember another rule. So if we have something like this, where it's 7x to the power of 3, this is like that Russian doll idea. You're going to differentiate the outside, then differentiate the inside. So the outside thing is something to the power of 3, so the 3 comes down, and 1 less than that is 2. But the inside stays the same. Then you differentiate the inside, and the derivative of 7x is just 7. And then you can tidy this up as you need to. 7 times 3 is 21, and so forth. But we're not going to go any further there. So when we're differentiating e to the power of 7x, that same idea stays the same. You pretend the 7x is part of the function, just like the 7x is inside the cubic function here. So you're first going to differentiate e to the something. I'll often say e to the blah, e to the something. Well, the derivative of e to the something is e to the something, just like e to the x is e to the x, e to the x is e to the x. So e to the 7x is e to the 7x. But that 7x, we're going to differentiate the inside now, just like we differentiated the 7x here. and had it times 7. So this is also going to be times 7. So you look at the entire function, e to the something, the derivative of that is e to the something times the derivative of the something. Now you can tidy it up if you want. It's as if there's a 1 there, and we'll often write it like this. Bring the 7 up front. 7 times 1 is 7, e to the 7x. So this works, this rule here, differentiating the e to the blah, e to the something rule first, then differentiating the exponent, applies regardless of what the exponent is. So if I'm looking at this one, the derivative of this, well, we have 3e to the something. So this is exactly like 5e to the x, where the derivative is 5e to the x. This, though, is 3e to the something. So the derivative of it is itself 3e to the something. Then differentiate the inside. Well, the inside is this exponent. And if you differentiate x squared, it's 2x. And differentiate negative 4x is negative 4. And so it's 2x to the minus 1. Now we can tidy this up. So 2x minus 1 and a 3 out front. This 3 can be multiplied by that. So 3 times 2x is 6x, and 3 times negative 12 is, or 3 times negative 4 is negative 12. So that gets rainbowed in, and then we have this part left over. And that's the derivative. I want you to know that this rule here of differentiating e to the something and then differentiating the exponent by itself is actually happening here as well. So e to the x is just derivative of that is e to the x. So if there's a 5, it's 5e to the x. And then you are actually differentiating the top there. If you differentiate x, you get a 1. So it's being multiplied by 1. But we don't write that because 1 times 5 is there, and so we rarely have that part as part of the answer. Okay, let's move on to e. And e, you've got actually two functions here. You have a quadratic x squared and an exponential e to the x. And we should remember, if we are taking the product of functions, we need to use the product rule. So the first function is x squared, and the second function is e to the x. So when we differentiate it, we need to use the product rule. Product rule is the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first, well, the derivative of x squared is 2x times the second. Leave it as is, e to the x. Plus the derivative of the second, well, the derivative of e to the x is just e to the x times the first, so x squared. So all of the same rules, the product rule, the quotient rule, power rule, all of those other rules apply with e to the x. We just now know the derivative of e to the x is e to the x. Now we can tidy this up a little bit. Now there's no like terms we can collect or anything like that. However, you will notice that there's an e to the x in both parts of these. So it's a common factor to both of these things. And this is going to happen all the time. This e to the x is going to be in both parts of the product rule because it's there because it's the original, and the derivative of e to the x is itself. And so it's always going to have that, which means you can always common factor out an e to the x. So if I bring the e to the x out, I'll be left with a 2x and a plus x squared. So we're always going to look to common factor in these questions. We sometimes didn't do that in other differentiation in earlier units, but in this one I'm going to demand that we always take out the e to the power of x because it will always be a constant or a common factor in both of these. So answers are going to have to be in factored form. Now because we're taking a common factor of e to the x, you should also pay attention to see if there are any other common factors. And you'll notice that there's also an x in both of these. You see there's an x in both of these. So that should also be a common factor. And so we're going to bring out an x as well, and we'll be left then with just a 2, and x squared divided by x is just x, and then we have that. We'll get to the point where we'll be able to see all of these common factors from the first line. So there's an e to the x and an e to the x and an x and x in both. So the common factor is x e to the x. Bring that out and you'll be left with a 2 plus an x. And make sure our answers are in factored form. Okay, so there's a bunch of differentiating with e to the power of x. I'm going to do one more example. And in this one, it's the classic question that I've been asking in every unit, and I promised I'd ask this in every unit. Find the equation of the tangent to the curve y equals x e to the x at x equals 2. So our goal is to get some equation of the tangent at this specific spot. So we know it's going to be y equals mx plus b. So if you recall, we need to find the slope and the y-intercept in order to do this. So to find the slope, well, of course, we're going to find the derivative, because the derivative is the equation that describes all the slopes of the tangents. So first we're going to differentiate y equals x e to the x. So what I see here is actually a product rule. I see the first function is a linear function, and the second function is the exponential function. So I have to use the product rule. Derivative of the first times the second plus the derivative of the second times the first. So what's the derivative of the first? Well, the derivative of x is just 1 times the second. It's just e to the x, plus the derivative of the second, which is e to the x, times the first, which is just x. I'm going to get into my habits of taking the common factor out. I see e to the x as a common factor in both, so that's going to come out, and I'll be left with 1 plus x. So this is the derivative of all the slopes of tangents. But I only want the specific slope of tangent when x equals 2. So I'm going to plug in 2 into my function. So e to the x becomes e to the 2, because the x is 2, and 1 plus x becomes 1 plus 2. Well, 1 plus 2 is 3, and so this is 3e squared. So the slope is the number 3e squared. Now remember, this is a number. It's not a variable. E is not a variable. It's like pi. Pi is not a variable. It's 3.14. E is not a variable. It's 2.178. Da, 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 da. So what you found is actually the slope, 3e to the 2. You can actually go to your calculator if you want, and you can find an e to the x button, and you could actually calculate this. So do e to the power of 2, and then multiply it by 3, and you'll get that the number is around 22.167. So the slope is actually around 22. But we're not going to write that long non-terminating decimal. We're going to leave it as 3e squared. That'll be more accurate than 22.167. Da, 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 da. Okay? And we'll use that as the slope. So if we have that as the slope, that can be put in to our y equals mx plus b. And there is the slope of 3e squared, 22 point whatever, x. So 3e squared x plus b. Next, we have to solve for b, which means we have to put in a y and an x and a y, so that we can figure out what b is. So how are we going to get that? Well, the x we know. The x is 2. So that part's easy. But how do I figure out what the y value is at 2? Well, remember, we're going to take the y and sub it into the original function. So we're going to take this 2 and plug it in here. So this will become a 2e to the 2. So when we plug 2 into the function, we get 2e squared. And the actual coordinate then is this, 2, comma, 2e squared. And that's a point. And that point can be subbed into the equation. So the y value is 2e squared. So that goes in there. The x value is the 2. The slope is 3e squared. There's my equal sign, 3e squared. Plus, I'm trying to figure out b. Now it's just a matter of doing a little bit of math and rearranging. Well, first 3 times 2 is 6e squared. So that becomes that. I want b by itself, so I have to get rid of the 6x squared. So I'm going to subtract 6e squared from both sides. And 2e squared minus 6e squared, this is like collecting like terms, is negative 4e squared. And we get another value for b. And remember, this is a number. You could punch that in your calculator, and it's roughly negative 29.556. But I'm not going to write down that number. I'm going to leave it as negative 4e squared. All right, I've done all my math. I've got my slope. I've got my y-intercept. And so I can put it into y equals mx plus b to get the equation of the tangent at x equals 2 of 3e squared x plus 4e squared. All right, so that's enough for now. If you would like to do some practice, you can go to page 302 out of our book, and we're going to answer number 3 on 4, just A, B, and D in 4, 8, and then 13 is a sneak peek at what we're going to do in a couple of days, but you should be able to do A, B, and C right now. So good luck with that practice, and thanks for watching.